Hello there and welcome back. Let me first find my little laser pointer here. All right, so this is part 2. We just talked about this whole concept of the system where the heat that arrives at the Earth from the sun has to be balanced out by the amount of heat that the Earth sends back, if you will, towards the sun. And this is achieved through what we call electromagnetic radiation. And the big picture story here is really that you live with electromagnetic radiation all the time. Your cell phone, for example, works on the basis of electromagnetic radiation. So anytime you get a phone call or you text or you do Snapchat or whatever you do with your phone is sending out or receiving electromagnetic radiation. And the key part here is that your eyes cannot see that radiation that's entering your phone or exiting your phone. And that's what we need to talk about. Let's first, the definition here, electromagnetic radiation or electromagnetic waves are a certain type of waves or certain type of radiation that can transport energy without going through something solid. So the perfect example here, once again, cell phone waves, radio waves, all that radiation that we use all the time, but it comes to us literally traveling through air or through nothing. It doesn't go through a solid medium. And the way we deal with this, the way we characterize energy here or radiation or waves is by its wavelength. Right? Let's get into that on the next slide. So here we have what we call the electromagnetic spectrum, electromagnetic radiation in all kinds of different wavelengths, from very short to much longer. This is from your book, figure 4-5. And it turns out that electromagnetic radiation with a wavelength between 0.4 and 0.7 micrometers just happens to be visible to humans. Because humans have sensors built into ourselves that can, if you will, measure or receive, quote unquote, see electromagnetic radiation of that particular wavelength. And those are our eyes. So all this other electromagnetic radiation is out there, except our eyes just simply don't work in these particular frequencies, in these particular wavelengths. They exist. However, our eyes are only working in this very narrow window here. That's what we call visible light. So next. Now, what about longer wavelengths? Infrared, microwaves, TV, radio, and so forth. Well, this is electromagnetic radiation that exists, but it's invisible to us in the sense that humans don't have any built-in sensors to receive them or see that particular electromagnetic radiation. But of course, your TV or your radio or your cell phone can see them. So for instance, if you were to call this phone number right now, which happens to be my phone number, what would happen is that you dial this number, your phone sends out electromagnetic radiation to a cell phone tower. That cell phone tower sends it to my phone, and my phone starts to ring. We can't see any of that happening, but that radiation is being transferred. Right? And the reason is that our eyes simply are not able to pick up or see or measure these longer wavelengths. Let's go to the short distance. Well, we have, for example, X-rays. Now, X-rays are also invisible to humans. Our eyes cannot see X-rays, but we can have special films, special sensors that can receive them. So if you've ever gotten an X-ray and you looked at that picture, you looked at that image, right? Those eyes or that film was able to receive that electromagnetic radiation and see, quote unquote, that electromagnetic radiation. So it's one of those stories where you can sort of imagine, if you will, when you sit in your car and you look at your radio and you have all these radio stations. However, your eyes can only tune to one particular radio station. The radio station 0.4 to 0.7 micrometers. That doesn't mean there aren't any radio stations here or down here. It's just your eyes are not working in that particular wavelength. Now, here's a fact of physics. Actually, two facts of physics. Everything emits electromagnetic radiation all the time. All right, that's one. And the amount or the intensity of that radiation and its wavelengths are determined by the temperature of the emitting body or the emitting object. So that's just something you have to memorize or you have to believe. Now, we could spend a few hours looking at a whole bunch of scary equations and derive that, but we can also just accept that. Because what's much more interesting is to now think about the consequences of this. And really and truly, I mean absolutely everything. As you're sitting there watching this video, you are emitting electromagnetic radiation. The pencil you're holding in your hand is emitting electromagnetic radiation. Everything. The chair you're sitting on, the table you're sitting at perhaps, the heater, your shoe you're wearing, the ground you're wearing, the ground you're walking on, the ice on the lake, whatever. That includes everything that floats around in the atmosphere. Clouds, water vapor, dust, raindrops, snowflakes, CO2 molecules. It doesn't matter if something is liquid or solid. Everything emits electromagnetic radiation all the time. So that's a little bit weird because as you're sitting there, as you're holding your pencil, as you're looking at that raindrop, you don't see anything. But that's just because our eyes don't work in this particular wavelength. Now, a hot object like the sun will emit more electromagnetic radiation, more energy, and it will do so at shorter wavelength. Conversely, a colder object, for example the Earth, will overall emit less energy, less electromagnetic radiation, and it will do so at longer wavelengths. And here's the equations that govern this. So here you have a slide that you're gonna just kind of have to memorize unless you want to deal with a lot of scary equations and take a couple of physics classes. Now, all right, here we go. We got a cup of coffee on the right. We got a soda with some ice cubes on the left. Both are objects. Both objects emit electromagnetic radiation. That's just the fact of physics. Now, of course, the coffee cup is hotter, so it will overall emit more electromagnetic radiation, and it will do so at shorter wavelengths. That cold drink you have in your hands also sends out electromagnetic radiation, but it's colder, so the wavelengths are longer, and overall the intensity is less. All right? So now let's go to the sun and the Earth. We got the sun here on the left schematically. We got the Earth on the right schematically. Again, they're both objects. Therefore, laws of physics would tell you both objects have to send out electromagnetic radiation. Now, of course, the sun, being much hotter than the Earth, will emit much more energy and do so at shorter wavelength. And here's our Earth, right? Emitting electromagnetic radiation, that's fine. Of course, the Earth is much colder than the sun, so overall there's less electromagnetic radiation, and it happens at longer wavelength. Now that's a little strange because you can't see this radiation. You can see the radiation from the sun. Why is that? Because it happens to be in wavelengths that our eyes can pick up. You cannot see this radiation because our eyes simply don't work in these wavelengths. Our eyes cannot tune, if you will, to this radio station, but it exists. All right, now, here we got our electromagnetic spectrum again. We have the sun. Surface temperature of the sun is about 11,000 degrees Fahrenheit. You do the physics on that, you realize, oh, okay, at that temperature, the sun will send out most of its heat, most of its electromagnetic radiation, most of its energy in a wavelength between 0.4 and 0.7 micrometers. And hey, guess what? That's exactly what our eyes can pick up, which of course makes a lot of sense from an evolutionary point of view. Our eyes should be tuned, if you will, to the most common, to the most intense, right, to the dominant wavelength. So that's the sun, 11,000 degrees Fahrenheit approximately. Well, let's do the math on the Earth, right? Well, the Earth has an average temperature of about 55 degrees Fahrenheit. Again, you can do the physics, and it turns out that Earth emits most of its electromagnetic radiation between about 5 and 30 micrometers in wavelength. And overall, of course, it's less because the Earth is colder. Now, once again, we cannot see these waves. We cannot see this radiation with our eyes, but we can see it with special films and special cameras, right? This is called infrared radiation. And here we have pictures from infrared cameras. So here's a good one. Right? You might be standing on a floor right now that has radiant floor heating in it. You can see these heating coils here as the brighter colors. Now, when you look at the floor right now, all you see is whatever, carpet, tile, whatever the covering of your floor is, right? You cannot see this heat. You cannot see this radiation. It exists. It's just our eyes are not tuned to that. And that's, of course, the whole secret about, or not secret, the whole physics behind infrared pictures. You can effectively see heat leaking that you can't see with your eyes because it's in a wavelength that we can't see. And the best example of that is, if you go back, is this. Right? If you remember these pictures, and I'm sure you do, this was the picture from the helicopters we saw of the boat in the dude's yard where one of the marathon bombers were hiding. This is what your eyes can see, because your eyes operate in the wavelength range from 0.4 to 0.7 micrometers. Now here is a similar picture of that boat with an infrared camera, a camera that can pick up the electromagnetic radiation, that can see the electromagnetic radiation emitted by the dude lying in the boat. This is our eyes, this is infrared eyes, if you will, picking up electromagnetic radiation that exists even though our eyes can't see it. So there you go. That was the physics of electromagnetic radiation in a nutshell. That's our cooling mechanism, right? Again, shortwave coming in from the sun. That's the heat from the sun we can see. Some of it is reflected, and here we go. These three squiggly arrows is the infrared radiation, electromagnetic radiation that the Earth is blasting into space. As we speak, as you're sitting there, you are part of that. You can't see it. Why? Because your eyes are not attuned to it. But that doesn't mean it doesn't exist. So that was part 2. We'll meet again in part 3.